Okay, so here's part 2 of the electron configuration lecture. So when we ended last time, I was saying that quantum numbers were not really the most convenient, let's say, method of keeping track of where electrons are in an atom at any given time. So in this half of the lecture, we're going to be looking at sort of the more convenient, the more everyday way to look at where electrons are in an atom. As you know, this is where the electrons are likely to be when they're not excited, in what's called their ground state, so not excited, and where they're likely to be 90% of the time. Of course, we can't know exactly where they are because quantum mechanics. So there are some rules that govern how electrons can be arranged in an atom. As you know, most atoms have multiple electrons, so we're going to see oftentimes multiple electrons following all of these rules. So the 3 rules, you do need to know the rule, but you don't necessarily need to know the name of the rule, if that makes sense. But the 3 are the Aufbau principle, the Pauli exclusion principle, named after Wolfgang Pauli, we saw a little bit ago, and then Hund's rule. So we'll talk about each of those in turn, what they mean to you as you try to describe the locations of electrons in atoms. So Aufbau comes from the German word for building up, and this was first described by, I think, Bohr. All of this stuff comes from right around Bohr's time, so it's not quite the quantum mechanical model yet, but there's a lot of overlap, as you'll see. So what the Aufbau principle, or the building up principle, says is that electrons have to occupy orbitals of lower energy first, and then they fill up to higher energy. So, for instance, the lowest energy orbitals are the 1s, or is the 1s. So what that means is that the first 2 electrons of any atom always start in their home location in the 1s orbital. Then the 2s, and then the 2p, and so on. It starts off relatively easy numerically, but as you'll see, because of the shapes of some of the orbitals, it doesn't always follow sort of the way you might expect. So this is an example of an Aufbau diagram. That's what it would say if it wasn't cut off there. And it just kind of shows, so the nucleus would be way down here at the bottom, and then you have your 1s would fill up first, then the 2s, then the 2p, because that's the next highest energy, then the 3s, then the 3p, and this is where stuff starts to get weird. The 4s is actually a little bit lower energy than the 3d, because the 4s is a spherical shape. Oh dear, sorry for my drawing skills. 4s, spherical shape. And the 3d, if you remember from the pictures, kind of does like a this kind of video. More or less like that. So there are parts of the 3D, these edges, that actually stick out farther from the nucleus than the 4s as a whole. So the 3D is actually slightly higher energy than the 4s. So it fills after, then the 4p, then the 5s, etc. So just having to remember that off the top of your head might be challenging because you will need to remember it. There is this little diagonal chart that can help you remember the filling order. So to make the diagonal chart, if you were to need to do so, maybe on a quiz, you just line up all your s's, starting with 1s because that's first. The p's don't start until 2, so you start with 2p, do all the p's. D doesn't start till 3, so you do the 3d. F doesn't start till 4, so you start at 4, the f's. And then you're making diagonal lines across And so to know the filling order, you just follow the arrow down to the bottom, and then you go up to the top of the next arrow. Follow it down to the bottom, up to the top of the next one. And so if you see when we get here, we go 3p6, 4s2, and then 3d10, 4p6, 5s2, 4d10, etc. After you do 6s, then you have another weirdness. 4f comes after 6s, as does 5d. So you need to be familiar with this rule. You need to be able to use it on a quiz next Friday. And you need to be able to recreate this, or you'll see later that there's another way that you can kind of show this same thing that some of you will prefer. So our next rule is Hund's rule. And what Hund's rule says is that in a set of orbitals, so let's say this is like the 2p, and p subshell always has 3 orbitals, which are represented by the 3 boxes, as opposed to the propellers. So in a set of orbitals, in this set of 2p orbitals, the electrons fill in such a way to give maximum parallel spins, maximum unpaired. Basically, each electron wants as much space as it can possibly have. So you can imagine maybe if you were traveling on a bus for a sport, if possible, you might each fill up one seat on the bus. You get your own seat before you had to double up. Or if it helps, you can imagine like you're on a train with people you don't know. You want to get perhaps a seat by yourself before you have to share with some random person on the train. So this arrangement, 1 in each box, is good. What you would not see is like up, down, up, and then an empty box. So electrons want to spread out because they repel, they're negative, right? So the next rule is what's called the Pauli exclusion principle, named after Wolfgang Pauli from Austria. And this refers to the electron spin quantum number that we talked about in the first video. So each orbital, each box, so S there's 1, P there's 3, D there's 5, F there's 7. Each orbital can hold maximum of 2 electrons. And because each electron needs to have its own particular address, its own particular set of 4 numbers, they can't be the same because if they're in the same exact orbital, they're going to have 3 numbers in common, right? They're going to be the same energy level, the same subshell, and the same box, basically. So to distinguish that, what we said with quantum numbers was that they had to have different electron spin quantum numbers. So the plus 1/2, minus 1/2 here. When we're doing this sort of visually, the way we show it instead is with arrows. So up arrow, down arrow. So they can't both be up or both down. You have to have one of each in a particular box. So here, we're just going to go through a few Aufbau diagrams, sort of looking at how the electrons fill up the boxes. In this particular scheme, it draws it, you can see, in the sort of increasing energy method. If you were to draw it in class, on a quiz maybe, what I would expect is that you would do 1s there, and then maybe you would have 2s here, and then your 2p next to it, and so on, to just take up a little bit more space. A little bit less space. So hydrogen just has 1 electron, so that electron's going to go in the lowest energy location, so it's the 1s box. Traditionally, you start with an up arrow before you do a down arrow. If you prefer to do down first, that's fine. So there's hydrogen. Here, helium has 2 electrons, so the first electron is going to be joined by a second, but this one has to be facing down because they have to have opposite spins. Skipping a little bit to nitrogen, so this is number 7. We have the same 2 electrons from hydrogen. Everybody always starts the same way. The only difference is as you get to the valence electrons effectively. So 2 in the 1s, 2 in the 2s, that gives us 4. Nitrogen has 7 total, so we need 3 more. So the next set of orbitals is the 2p. So you can see our 3 boxes there. Following the bus rule, or Hund's rule, instead of all cramming together, the electrons spread out. So you have 1 in each box of the 2p. And then that's all 7 of your orbitals for nitrogen. So using the sort of box and arrow method is handy. It gives you a nice visual of where the electrons are located in the atom. But if you were to go to write the electron configuration for one of the bigger elements, like francium or something, that would take a long time. It would be a lot of boxes and a lot of arrows, and you would probably be very cross. So instead of always writing the box notation, there's another sort of shorter way. It's called standard notation. So what you see here is the standard notation for fluorine. Fluorine has 9 electrons. It's number 9 on the periodic table. And so instead of writing it, with boxes and arrows, the energy level, N, is a big number in front, like a coefficient. Then the sublevel is written as its letter, S, P, D, or F. And then the number of electrons in that sublevel is written as an exponent. So for fluorine, with its 9 electrons, the first 2 electrons go in the 1s, the next 2 go in the 2s, so that gives us 4, and then the last 5 electrons would go in the 2p. So energy level, subshell, number of electrons. And all atoms always start out this same way. They always start out 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc. So even this, if you're doing a bigger atom, can get a little bit repetitive because it starts out the same way. Another thing to note, if you add up all of these electrons, or all of these numbers, that will equal the total number of electrons. So fluorine has 9, so 5 plus 2 is 7 plus 2 is 9. So when you're trying to keep track, if you count those exponents, that'll get you to your total value. So even with the notation that we just looked at, if you had to do a big element like francium or something, oganesson, that would take a long time, 118 electrons. So there's a shorthand that we refer to as noble gas notation. So because electrons fill up shells in the same way all the time, you can kind of use noble gases as a shorthand so as not to have to write out everything always starting at 1s, 2s, 2p, etc. So if you were to look at fluorine, say, the noble gas that comes before fluorine is helium. Okay, it's got to be the noble gas that comes before the element, so with a smaller number. And helium has a 1s2 electron configuration, which means it's full. Its shell is full. Neon, on the other hand, has a 2p6 configuration, meaning, you guessed it, it's full. All the rest of the noble gases, excepting helium, are all going to have whatever energy level they're in, P6. So you can use that as a shortcut and just write everything that's different after the noble gas. Okay, so for fluorine, you write And then you write the noble gas in a bracket. So for fluorine, it's helium. Then, anything additional. The nice thing, and you can see this on this particular periodic table, it has what's called the period numbers on here. On the first row, the first energy level is filling up. The second row, it's the second energy level. The third row, it's the third, and so on. So you can simply count down from the top, and it's 2p6, 3p6, 4p6, 5p6, 6p6, 7p6. And then you just go whatever comes after that. So let's do an example. How about manganese, Mn25. So, manganese is 25. The noble gas that precedes it then is argon, which is number 18. So the first thing to do is write argon, Ar, in a bracket. Argon is in the third row, 1, 2, 3, which means that manganese is going to be in the fourth row. We're going to start with 4s2. So that gets us from 18 to 20 electrons. After 4s on the diagonal chart, we have 3d. Okay, we're already showing 20 electrons. Argon is 18. 4s2 is 2 more, so that's 20. So we need 5 more electrons. So it's going to be 3d5. So you just use the noble gas as a starting point to kind of shortcut and only have to write what comes after that particular noble gas. So this shows how the periodic table itself corresponds with electron configuration, because it's kind of magnificent. So if you notice, the first row, row 1, represents the 1s filling, and there's just 2 elements there because there are only 2 possible electrons in the 1s. Everything else in the first 2 blocks of the periodic table represents the s orbitals because they can only have 2 electrons. Over on the other side, we go from 2s to 2p, right? This whole block with 6 elements across in it is the p block. So this is where the p orbitals are filling up, one after another. That's how you know this column, except for helium, is always whatever p6. If you remember from the diagonal chart, 3d fills up after 4s. So the first d orbital with 10 across that we see is the 3d. That fits in right there. So that can help you remember 4s, then 3d, then 4p. So this is kind of the alternative. If you don't want to try and remember the diagonal chart, you can use the periodic table. In here, from 6s, if you remember from the diagonal chart, we go to 4f. So that fits right in between 6s and 5d. It just makes the periodic table really long if they stick the f block in, and so they kind of pull it out to the bottom. Likewise, after the 7s and before the 6d comes the 5f. So those slot in there and would really, spread out the periodic table much more. That's why you find them at the bottom. But there you go. That's why the periodic table is such an interesting shape, because it matches with the electron configurations that we just talked about it. Fun, yeah? It is. It's very exciting. Okay. As you might expect in chemistry, there are exceptions. The sort of nice thing about these particular exceptions is that they really prove the rule, right? Occasionally, and these are just a couple of examples, and they're going to come up later on this year. That's why I want to make sure and talk about them now. Is that occasionally the Aufbau rule isn't followed. And as you get to bigger and bigger elements, it's followed less and less closely. But there are some electron configurations that are more favorable than others, even accepting the whole Aufbau rule. So 2 exceptions that I want you to be familiar with are that of chromium and of copper. So chromium, we would expect, it has 24 electrons. So we would expect, if you were following the Aufbau rule, that it would have 2 in the 4s and 3 in the 4d. D orbitals can hold up to 10 electrons. And what we find is that actually chromium will bump up an electron into the D to make it half full. So it becomes, in reality, 4s1, 3d5. Half full and full subshells, especially with the bigger shells like D or F, are more stable than having a full S and an almost full D or an almost half full D. So electrons will get sort of moved around just a little bit to if they're close to having these half full or full subshell conditions. When we start to talk about transition metal ions, like why iron can be +3 or +2, or why copper can be +1 or +2, we're going to come back to this electron configuration idea. So this is just a little preview of exciting things to come. That concludes our electron configuration lecture. I hope you have stayed awake through all of it. You will have some good time to practice in class over the next weeks. So do your best. Bye.